Hi, let's now discuss the symmetry associated with identical particles. We shall talk about the identity of particles and also what's called the indistinguishability principle. So far, we discussed certain symmetries which come from the properties of space and time. We talked about space translation symmetry, which arises from the homogeneity of space. We talked about time translation symmetry, and it comes because of the homogeneity of time. The rotational symmetry was associated with isotropy of space. So these are related to the properties of space and time. Now we shall discuss a different type of symmetry, and we encounter such symmetry in quantum mechanical behavior of a system of identical particles. Let's start by clarifying the term identical when we apply it to a group of particles. Two particles are said to be identical if there is no experiment that can distinguish between them. So identical particles are indistinguishable. And all identical particles share the same intrinsic properties. For example, mass, charge, spin, magnetic moments, etc. These are the same for all identical particles. If any of these were different, we could distinguish them experimentally. All electrons, for example, are identical. All electrons have the same charge, the same mass, they are all spin half, etc. Now, different electrons can be in different dynamical states. For example, one electron could be in a spin up state and the other is in a spin down state. But we would still consider them identical. We have learned that the best we can do to describe quantum mechanical particles is to specify a complete set of commuting observables or a complete set of compatible observables. Now, each of the identical particles that we are considering may have different eigenvalues of the operators in the complete commuting set of observables, but we would still consider them as identical particles. Okay, this means that for two particles to be identical, they must be identical in the physical attributes that are not described as eigenvalues of the complete commuting set of observables. They need not be identical in the physical attributes that are described as eigenvalues of the complete commuting set of observables. Okay, all other physical properties which are not eigenvalues of the complete commuting set of observables must be the same for the identical particles. Okay. This criterion for the identity of particles has an interesting consequence. Let's consider particles that are different from the viewpoint of their physical attributes such as mass and electric charge. Normally we cannot consider them as identical particles. But if we could associate this mass and electric charge to the eigenvalues of one or more observables that commute with the Hamiltonian of the system, then different mass and electric charge correspond to different eigenvalues of operators in the complete commuting set of observables. And then we can consider these particles as identical. So particles that are different from the viewpoint of their physical attributes, such as mass and electric charge, could be considered identical if we could ascribe the differences to the different eigenvalues of one or more observables that commute with the Hamiltonian of the system. A good example for this technique is the case of the proton and the neutron. We know that the proton is positively charged while the neutron has no charge. In fact, their masses are also different, but the difference is small, and in certain cases we can neglect the difference. And the proton and the neutron can be described as two different states of the same particle called the nucleon. Okay? We can do this by introducing another observable, a new observable called isospin. All right, it has the name isospin because it's analogous to the spin. So what we do is that for the nucleon, we assign an isospin half. Okay, T is equal to half. So the proton and the neutron correspond to two possible values for the Z component of isospin. Okay, and this could be plus half and minus half. Now you might easily see why this is called isospin. It's similar to the case of spin because electrons are spin half particles and they can have different Z components of spin. They can have either plus half along the Z direction or minus half along the Z direction. In the same way, we say that nucleon is a half isospin particle and the proton and the neutron are different dynamical states of the nucleon with eigenvalues plus half and minus half. So just like an upspin electron and a downspin electron are different dynamical states of the spin half electron, we can say that a plus half isospin and minus half isospin particles, the proton and the neutron, are different dynamical states of the isospin half nucleon. Okay. But this description of the proton and the neutron as different states of the same particle is not valid when electromagnetic interaction is involved. The reason is that the Hamiltonian in the case of electromagnetic interaction does not commute with isospin. So we say that isospin is not conserved for electromagnetic interactions. But in the case of strong interaction, the strong interaction Hamiltonian commutes with isospin. This actually means that the strong interaction Hamiltonian does not see charge. It acts equally on neutral charge neutron and positively charged proton. In other words, the strong interaction acts the same way on the proton and the neutron. In that case, we can actually consider proton and neutron as different states of the same particle. You may discuss these things in more detail in your particle physics class. Let's now get back to the symmetry associated with the system of identical particles. Okay, we shall see that an important aspect of the symmetry associated with the system of identical particles is that it is intimately related to the spin of the particles. And this relation has important consequences. In fact, this is the reason why particles of different spin obey different statistics. You might have already learned that spin half particles obey the Fermi-Dirac statistics, whereas the integral spin particles or bosons obey Bose-Einstein statistics. We will be discussing these things in a little bit more detail. Okay? But the important point is that we will not be able to ignore the spin as we have done so far in most of our discussions. Right? So far we just said let's ignore spin and talk about the energy and angular momentum, etc. But when we discuss the identity of particles, we shall not be able to ignore the spin as we have done so far. Okay. Now we know the meaning of the term identical particles as used in quantum mechanics. Let's now discuss what's known as the indistinguishability principle. We know that in classical mechanics, identical particles, at least in principle, can be distinguished from one another. This can be done either by observing their individual trajectories or by means of labeling them. You could label if you have two particles with the same intrinsic properties. You could label one particle as particle 1 and the other particle as particle 2. You could in principle color the first particle with blue and the second particle with red. All these things can be done because in classical mechanics, at least in principle again, observation or labeling does not affect the classical dynamics of the particles. Okay, so an act of observation does not change the time evolution of a particle in classical mechanics. It does not change the path of a classical particle. So in classical mechanics, the assumption is that we can make an observation on the classical mechanical system without disturbing it. But we already know that this does not work in quantum mechanics because as we have seen in the measurement postulate, the quantum mechanical system evolves differently depending on whether or not you are making an observation. That is, when we are not observing, the system evolves according to Schrödinger equation, which is a unitary evolution. But when we make a measurement or when we observe a quantum mechanical system, something else happens. The measurement postulate says that the state of the quantum mechanical system actually changes during a measurement. So in quantum mechanics, the state of the system, let's say ket alpha, it evolves according to the Schrödinger equation when you are not observing it. But when you are making a measurement, say of an observable A, right? If you're making a measurement of an observable A on this state, then we know that the state of the system changes from ket alpha to ket A prime. And this change is not according to Schrödinger equation. This was the measurement postulate. This means that the strategy of distinguishing identical particles in classical mechanics does not work in the case of quantum mechanical systems. So in quantum mechanics, identical particles are truly indistinguishable. There's no way of distinguishing identical particles in quantum mechanics. The best we can do is to specify a complete set of commuting observables. Nothing more can be done in the case of quantum mechanical particles. We cannot say anything more than a complete set of commuting observables. And in particular, you cannot label the particles by coloring it red or blue, because that would amount to specifying something more than a complete set of commuting observables, and this is not allowed by the rules of quantum mechanics. Okay, we cannot follow the trajectory of a quantum mechanical particle either, because to follow the trajectory, you would actually need a position measurement at each instant of time, and this necessarily disturbs the quantum mechanical system. So the assumption in classical mechanics that you can actually make a measurement without disturbing the system is not valid in quantum mechanics, because as we have already seen, measurements change quantum mechanical states of the system, and this change is random. It is not according to the Schrödinger equation. So identical particles are truly indistinguishable in quantum mechanics. An observer cannot distinguish them. Nature itself does not distinguish identical particles in quantum mechanics. For example, consider the scattering of protons by protons. So let's say we have a target proton and a projectile proton. They scatter, and let's say that we have detectors which can detect protons after scattering. Okay. But the proton that comes to the detector could either be the projectile or the target proton, but it would be impossible to tell them apart. There's no way of telling whether it's the projectile proton or whether it's the target proton that has registered in our detector. And this indistinguishability actually has measurable consequences, as we shall see soon. Similarly, you can think of a helium atom. We can consider the state of a helium atom in which one of the electrons is in the state, say, phi alpha, and the other one is in the state phi beta. We could interchange these electrons, but the interchanged state will be indistinguishable from the previous state of the helium atom. This is because electrons are completely identical. Okay. This inability to tell apart the particles from one another in a system of identical particles is embodied in the principle of indistinguishability of identical particles. So if you want to describe a system of identical particles using quantum mechanics, you must incorporate the indistinguishability of them into the formulation. That is, quantum mechanics of a system of identical particles should be so formulated as to be consistent with the principle of indistinguishability. For example, in the scattering problem that we just mentioned before, the experiment, no experiment can distinguish between the projectile and the target. So in quantum mechanical calculation of the scattering cross section, also, no distinction should be permitted between the projectile and the target. As I mentioned before, this indistinguishability has serious consequences in quantum mechanics, and we have to emphasize that the significance of the principle of indistinguishability is far deeper in quantum mechanics than it is in classical mechanics. The peculiar laws underlying quantum mechanics, in particular the principle of superposition, are responsible for this. For example, let's consider a classical mechanical situation of scattering in which we are scattering two identical particles. This could be billiard balls. So let's say that there are two billiard balls which are identical. Okay, these are classical mechanical particles and they scatter off each other. We are not looking at it. We are not labeling these billiard balls. And let's say we need to find the probability that one of the billiard balls is found at this region, in this region. So we know that there are two possibilities. Either this billiard ball can reach this region or the target billiard ball could reach this region. Okay. So if you want to calculate the probability that one of the billiard balls reaches here, we just have to add the probabilities for each possibility. Okay, let's say that there's a given probability P1 that this particle reaches the detector. Let's say we have some sort of a detector for billiard balls. Okay, and if P2 is the probability that the target billiard ball or the second billiard ball reaches this detector, then the probabilities, since we cannot distinguish them, we can only talk about the probability that one of the billiard balls reaches at this point. We just have to add the probabilities for both possibilities. But in quantum mechanics, we have to add the probability amplitudes for each possibility. So if a given measurement can occur in two different ways, in quantum mechanics, the total probability is found by adding the probability amplitudes for each of the possibilities and then taking the modulus square. In the case of classical particles, since probabilities are positive definite, there's no problem. Okay, but probability amplitudes in quantum mechanics can be complex numbers. They can be positive, negative, or even imaginary. So some of the probability amplitudes can cancel each other, and so we have a completely different situation from the classical mechanical case. Okay, let's come back to the example of proton-proton scattering. The indistinguishability between the projectile and the target proton implies only the following in classical mechanics. In classical mechanics, if we cannot distinguish between the target and the projectile, then the observed cross-section would be the sum of the cross-sections corresponding to two different cases. One case in which the projectile reaches the detector, and the second case where the target reaches the projectile. In classical mechanics, we just have to add these cross-sections. The two possibilities that we mentioned are shown here. Okay, this is the first possibility. In this possibility, it's the projectile that reaches the detector here. Okay, so this projectile is labeled as 1, and this projectile scatters off the target and it reaches the detector here. Right, the target gets scattered in this direction. Right, so this is shown in the center of mass system. But there's another possibility. The second possibility is that the target particle actually scatters to the detector. Right, it's possible that we measure the target particle in the detector. In that case, particle 1 or the projectile would go this way and the target goes towards the detector. So let's say that this process in which the projectile reaches the detector has a certain cross section. Okay, let's say that this process also has a certain cross section. If these were classical particles, what we need to do to get the total cross section would be to add these separate cross sections. So if these were classical particles, we just have to add the cross sections corresponding to these separate possibilities. Okay. In the case of quantum mechanics, we calculate scattering cross-section by taking the modulus square of scattering amplitudes. And in the case of proton-proton scattering, quantum mechanics says that we have to add the scattering amplitudes corresponding to the two cases to find the total scattering amplitude, and then take the modulus square of the total scattering amplitude to find the scattering cross-section. So there's no simple relationship between the quantum mechanical cross-section and the cross-sections corresponding to separate cases A and B. In classical mechanics, you just add the cross-sections corresponding to the different possibilities. But in quantum mechanics, it's not so simple. We first have to find the scattering amplitudes corresponding to each possibility, add them to find the total scattering amplitude, and then take the modulus square of the total scattering amplitude to find the observed scattering cross section. Okay, and this complicates things. As I said before, in certain cases, these amplitudes can add up to 0, which never happens if we are adding probabilities. That's why we mentioned earlier that indistinguishability of particles has a deeper significance in quantum mechanics than in classical mechanics. In quantum mechanics, this indistinguishability is really fundamental. In this class, we learned the meaning of the term identical particles in quantum mechanics. We then discussed the indistinguishability principle, which basically said that the rules of quantum mechanics do not allow us to distinguish identical particles, to distinguish between identical particles. So, if we want to formulate quantum mechanics for a system of identical particles, we should do it in a way that is consistent with the indistinguishability principle. In the next class, we shall discuss the formulation of quantum mechanics for a system of identical particles. I hope you have followed the class. Thank you.